lid of a bottle is screwed on too tightly. The bottle is immersed in hot water, which makes the lid come off easily. This happens because when the metallic lid comes in contact with heat, it tends to expand, thus loosening up and coming off easily. Similarly, in a liquid-in-glass thermometer which makes use of mercury, we see that mercury expands when the thermometer measures high temperatures and contracts again when it is used to measure a low temperature. We know that most objects expand on heating and shrink when cooled. Thus, changing the temperature leads to a change in dimensions of the object. When change occurs in the length of the object, we call it linear expansion. Similarly, if area of the object changes, the term used is area expansion, and if volume changes, then volume expansion. Let us consider a long rod made up of metal. For a small change in temperature, delta T, the change in length delta L by L is directly proportional to delta T. Therefore, delta L by L equals alpha L delta T. Here, alpha L is a constant of proportionality, known as the coefficient of linear expansion. The table here lists the values for the coefficient of linear expansion for some materials in the range of 0 degrees Celsius to 100 degrees Celsius. Looking at this table, it can be seen that metals seem to have relatively higher values for the coefficient of linear expansion and thus expand more. For a small change in temperature delta T, the change in length delta L by L is directly proportional to delta T. Similarly, change in the volume delta V by V of an object with a change in temperature delta T are proportional to each other. We can thus define another constant of proportionality, known as the coefficient of volume expansion, alpha V, as alpha V equals delta V by V into 1 by delta T. In this case, alpha V is also a characteristic property of the substance, but it is not a constant in the strict sense. The value of alpha V depends on temperature and is seen to become constant only at high temperatures. The table given here shows the value of alpha V for some substances in the range of temperatures between 0 degrees C and 100 degrees C. Water exhibits anomalous behavior in this regard. It seems to contract on heating between the temperatures 0 degrees C and 4 degrees C. Thus, water, when cooled, keeps decreasing in volume until it gets to 4 degrees C. After it passes this temperature, volume increases and the density decreases. Water, thus, has maximum density at 4 degrees C. This property of water is extremely important environmentally. The surface of the water in a lake in contact with the atmosphere freezes first and forms a layer of ice which insulates the lower layers from the cold. As a result, the lake does not freeze from the inside, and the ecosystem inside the lake manages to survive. At the same temperature, gases expand more than solids or liquids do. While the coefficient of volume expansion for liquids is more or less independent of the temperature, it is highly dependent on temperature in the case of gases. For an ideal gas, the coefficient of volume expansion can be arrived at from the ideal gas equation, PV equals mu RT. When pressure is constant, P delta V equals mu R delta T. Dividing this equation by the previous one, we get delta V by V equals delta T by T, that is, alpha V equals 1 by T for ideal gases. Thus, for gases, the coefficient of volume expansion decreases with an increase in temperature. Let us now try to investigate the relationship between the coefficient of linear expansion and their coefficient of volume expansion. Assume a cube of length of side L. This cube expands uniformly in all directions when its temperature increases by delta T. Thus, delta L equals alpha L L delta T, or delta V equals L plus delta L whole cubed minus L cubed, which is approximately equal to 3L square delta L. Since delta L is extremely small compared to L, we neglect the terms delta L square and delta L cubed. Fixing the ends of a metal body rigidly to prevent Thermal expansion leads to the development of thermal stress in the rod. Let us consider an example. A steel rail of length 5 meters and cross-sectional area of 40 centimeters square is prevented from expanding while temperature rises by 10 degrees C. The coefficient of linear expansion of steel from the table we saw earlier is alpha L steel equals 1.2 into 10 raised to minus 5 per Kelvin. Compressive strain is given by delta L by L equals alpha L steel delta T equals 1.2 into 10 raised to minus 5 into 10 equals 1.2 into 10 raised to minus 4. Steel has Young's modulus Y steel equals 2 into 10 raised to 11 Newton per meter square. Thermal stress developed is given by delta F by A equals Y steel into delta L by L equals 2.4 into 10 raised to 7 Newton per meter square. This corresponds to an external force of delta F equals AY steel into delta L by L equals 2.4 into 10 raised to 7 into 40 into 10 raised to minus 4, which is approximately equal to 10 raised to 5 newtons. A force of this magnitude is capable of bending the rod. This is the reason why train tracks have gaps in between them. During summer, when the tracks heat up, they expand. If space is not provided for them to expand, the tracks would bend themselves and cause accidents.